To obtain an ripple-free output of a modulating signal at the output of a detector, it is very important to choose this RC time constant. We know that the capacitor charges through a diode D and RS when diode is on, and the capacitor discharges through a load resistor RL when the diode is off. That is, the charging time constant Rs into C. It depends upon this charging time constant Rs into C, wherein the period is 1 over Fc. So what is that Fc? Fc is nothing but a frequency of an carrier signal. RSC should be less than 1 over Fc. This is how the charging time constant should be there, and the discharging time constant is RL into C. So it should be so long so that the capacitor discharges through the resistor RL, and it should be short compared to 1 by maximum frequency of a modulating signal. Mathematically, we can write it in this equation form, that is 1 over Fc is less than RLC and it is less than 1 over Fm. Fc is carrier signal frequency and Fm is modulating signal frequency. There are two types of distortions when the RC time constant is not chosen properly. First one is a diagonal clipping and the second one is negative peak clipping. So what happens in this diagonal clipping? So in this diagram, you can see that, so this wave, that is nothing but a low frequency wave. This is the output without clipping. That is wherein the diagonal wave is not been clipped. Clipped in the sense it is been removed. You can see one more signal, that is the dotted line, wherein we are not getting back the original information signal, wherein some information is been clipped, that is which has been removed. When this happens, if the discharging time constant RLC is too large, if the discharging time constant of a capacitor is too large, then it will start discharging in such a way that the diagonal wave, the particular wave will be clipped off. Then RC circuit cannot follow fast changes in a modulating signal envelope. And the next one is negative peak clipping. So in this negative peak clipping, we can see that this negative wave is being clipped off or it is being removed. You can see that two signals wherein it is clearly showing that the negative form is being clipped off or it is being removed, which means that some of the information will be removed. When this condition happens, if the modulation index is greater than 1, then the modulation is called as an overmodulation. If this modulation index on the output side of a detector is higher than the modulation index on its input side, then negative peak clipping will be formed. After seeing the generations of AM as well as AM demodulators, now at the end we'll be looking at the advantages of AM. So as we have seen, AM is very easy to implement, and the receivers are simple and it is cheap. So it is most cost effective. But there are some disadvantages in AM, that is in terms of power. And it is prone to high levels of noise. It requires a bandwidth which is equal to twice the highest audio frequency used. After seeing advantages and disadvantages, there are few applications of AM. That is, these are being used in radio broadcasting as well as in picture transmission in television systems. There are few limitations of AM. So what are those? The first one is the power is wasted in the transmitted signal. We know that in an AM signal, so there is an carrier signal at a frequency Fc, and there are two side bands, that is upper sideband and lower sideband. And we also know that this carrier signal will not contribute anything to the information because it does not carry any information. The information is present only in these two sidebands, and these two sidebands, the information is identical also. Therefore, lot of power will be used in transmitting all these signals, that is the carrier signal as well as the sidebands. Most of the transmitted power is in carrier signal, that is for 100% modulation, that is for mu is equals to 1 or m is equals to 1, 1/3 of the total power will be used in sidebands, but whereas 2/3 of the total power will be present in the carrier signal. And now the carrier signal, as we know that it does not consist of any information. And the second one is bandwidth. As we know that the bandwidth occupied by this AM wave is nothing but 2 times the modulating signal frequency. And the third one is a very important thing. We know that in an AM wave, any amplitude variation, or here the modulation takes place by an variation in the amplitude. When the signal is being transmitted from a transmitter to a receiver through a communication channel, some noise can get added. The noise will change these amplitudes of the envelope of an AM wave in any random manner. As the information contained in amplitude variation of an AM wave, the noise will change. This noise can change the information content in an AM signal. Hence, the performance of an AM is poor in presence of noise. Thank you.